So the next thing that I want to talk about today is just go back to presentation slides that Josh gave us. And now I feel we have a better understanding of, let me find it first. Now we have a better understanding, I think, of how the model is being set up. So, yeah. So, well, the model, I should say how hierarchical model is set up. So I do want to go back to parts of the model that they have been fitting in their project. And I want you to just talk to your neighbors again about, well, how things are being set up. And then especially now we know there might be different ways of sharing parameters. And I want you to discuss, say, how exactly things are being shared. So this, again, is one particular, I think, one particular condition. And, right, I think it's, so there are 9 in total. And this is the one particular condition. And they're modeling the response time is a normal density, and then the mean of that, they were using a power function for that, and then they talk about what does it mean to have alpha, beta, and gamma in the model, and then this is the, and then of course for the normal density for the response time, they also have the sigma, which they put a gamma distribution. So this is for 1. Okay, and then the sharing, one type of sharing that they talk about. So this is before looking at the individual data. This is still average data. And one thing that he talked about is now we have 9 different curves, and meaning that you have, let's see, 9 different curves here. So each curve has this alpha, beta, and gamma 3 parameters, right? So I think that was when Josh was saying that, okay, we have 27 parameters. And then if you think about sigma, that's one other parameter as well in their model. But then he started talking about this sharing. And I think this plot is supposed, this graph is trying to show us that all of the beta the beta parameters in different conditions and different words, it's using the same beta distribution, AB, right? And then similarly, on the left, you have this gamma for alpha, and on the right, you have this gamma for gamma. Okay, so I want you to just like quickly discuss with your neighbors now what is being shared and what kind of assumption is being made, and then just think through how many parameters are there in this particular model when they're dealing with it, based on our understanding so far. Okay, yeah, that's the plot. Okay, so what do you think? So first of all, there are 3 letters that we're testing, and then so for each, say for n, they have the 3 different curves. I think it's because there's 3 different conditions, right? The known words, the novel words, and the scrambled words. So it's just like they put everything together. So there are 9 different curves that they're trying to estimate. So, and we know for each of them, there's an alpha, there's a beta, and there's a gamma. And I don't know actually whether the sigma are being shared or not. It's hard to tell, but let's say they are, so for each of the curve, we have a sigma, which is the standard deviation for the normal. And let's say they all come from the same distribution as well, just for now. So, so how many parameters are there in total? What do you think? And what are being shared? Yeah, Eric?
There will be 27.
So why?
Total parameters. Because for each alpha, beta, and gamma, there's 9 separate distributions for each one. And like one of the assumptions that we had to make was that, so like in this case, that each beta value, the beta distribution would be the same across all of them, and then the same for alpha and gamma.
So what do you mean? What do you mean by when it's the same beta for all?
Or like they're generated from the same beta distribution.
Yeah. So beta, say like right now on the screen is this beta. It's a unknown parameter, and we have 9 of them. They each of the curve. And what this is saying, their notation here is that all of them. So if we are able to use definitely different from what they write, I'm sure, but just trying to conform to what we've been writing. Let's say, let's still try to use J as the group. In this case, it's more about word, the combination of word and condition. Okay? And then there are 9 in total. Okay? So if we're working with this beta unknown parameter, which is in the power function, we're saying that all of them comes from the same beta distribution AB, right? Yes. And similarly, if we have alpha, if we look at alpha, so alpha J all comes from the same gamma. I don't know the notation. Let's just use alpha. Let's use. Let's do A alpha and B alpha here. And then similarly, if you look at the gamma parameter in each of the 9 curves, so it's A gamma and B gamma. So I think by now it's easier to see how the hierarchy, or like the 2-stage prior, if we try to put it in the wording that we've been using, how it is being specified, right? So for that sigma, I don't know. So if we only consider alpha, beta, and gamma, I think there are 27 parameters in total. In fact, if we have all of those as unknown as well, we have 6 hyperparameters, right? And they're all associated with the beta and the 2 gamma distributions that we have, okay? In terms of that sigma, if we don't know exactly how it is done, we should look at the JEX, probably that will help us a lot. And so there are really, like, right now, maybe 2 ways that we know so far what you can do. One thing is each sigma j, let's just do, I think they did a gamma distribution, right? Yeah. So say it's a gamma of, so it's A sigma and B sigma. If we do this parameter, or like the sequence of this parameter, 9 of them are not being treated differently from the other ones, okay? We're still being shared in a hierarchical way. Whereas if we do something that we have been doing in our K-drama example, then that was just saying that, okay, sigma is the only parameter, the single one parameter being shared across all of the 9 curves, but it's not being shared in a hierarchical way, right? We're just saying that that's the only standard deviation. So if you do this, so I'm going to use the same notation, just use A sigma and B sigma, but keep in mind that these are different, okay? These are different assumptions. And then, of course, you're going to have, in this case, if you do the approach 1, then what you're going to have 9 more parameters to add to your model, and then 2 more hyperparameters to add, okay? Whereas if you go approach number 2, then sigma will be functioning the way that we have been seeing. Well, they give a different prior distribution here, which is fine. But then that means we only have 1 more parameter to work with, and then 2 more hyperparameters to work with. Okay, yeah. Any other way that you think might make sense, like to deal with sigma in this case? I presented 2, just based on one following what they've been doing with the other parameters. The other one is go back to what we have been doing. But do you see any other ways of dealing with this sigma? So again, sigma is the measuring the spread of the curve, or like of the learning, say, in each combination of the word and the condition. So do you see any other ways that is possible? I will pause here and then let you think about it. I mean, not that like this 2 are wrong. There are many other ways you can do it. I just want you to start thinking how hierarchical model can be set up in different situations. Okay, any idea? Suggestions or discussions? There's no right or wrong, so just don't be afraid speaking up. What?
We were talking about breaking them up, like between the learning groups, so like the N, I, and W.
Mm-hmm.
So like not generalizing across all of them, but just like treating each group the same as like the other ones in the same group.
So you're saying that within, say like within the N, I have this, okay, so notation, let's see. So you're saying that within the N, I have this sigma j follow a gamma distribution, okay? Good. Okay, so, well, the notation will get like too much, so I will just leave it as it is. And within the I, we do sigma j, and then within the W, we do sigma j, right? So what does that tell us? Like, what are the, so what kind of assumptions you're making when you are breaking them within the words?
That like everybody in that group is being treated the same. So like, yeah, basically like everybody with scrambled letters is gonna be, they have like similar variability. Something like that.
I see. Okay, yeah, so maybe, okay, because there are so many different curves here, my understanding, correct me if I'm wrong, I thought it's for different letter, like N, I, and W, each of the curve represent a condition, right? So if you're sharing sigma j across the three curves in the letter N, I think you're making the assumption that the variability in the learning for this word, I shouldn't say regardless of the condition, but it's for this particular word N, which is the starting, right? I mean, that's I forgot the term that they use it, but like N is always the starting, like it's NIW always is the triplet like happening this way. So if we do this, I think we're saying that for the novel words, known words, and then the scrambled words, the three different conditions, we think that the variability sigma j for this word N comes from the same distribution, okay? And similarly, we do that for I, and then we do that for W. Okay, so I think that's what the assumption is, but can I just comment about, well, for a different condition, if you think that it's for a different condition, or I should say for a given condition, you think the spread, which is measured by the sigma, might come from the same distribution, then what you would do is for, okay, then I also like just for example, let's say all, like say the three curves in each word. Let's say the first one is the known words, the second one is the novel words, the third one is the scramble. If we label them in this way, okay, and yes, right, if we do that, then one thing we can do, following what Precious commented earlier, is we think that in the same condition of known words condition, the spread comes from the same distribution. Okay, so that means, okay, sorry about all of the curves here, it's just too much, but I'm trying to say that another way of doing this is thinking within each condition, right? That might make more sense. I don't really know. Maybe like grouping them by words make more sense, especially like, well, you might want to group this two together. I forgot. Maybe not so much, because N is always like appears the first, and then you know immediately that after that will be I. So maybe this overall going to have a higher learning curve. I don't know. But again, I think based on the comments just now, we at least can think of two more ways of doing those sigma. And in fact, I think for the alpha, beta, and gamma, you might do things in this way as well. Depends on like the particular thing, like the learning theory that I want to test for. I think you can come up with many different ways of dealing with the model. But the key is we need to know that, say, for what we talked about at the beginning, this two are two different ways of sharing. Okay? And then what they mean, I mean, they mean different things, and then in terms of estimation and in terms of the number of parameters that you're adding to the model, they all mean differently. And that also means in the end, when you're trying to summarize the results, they mean different things. Okay, so that's, so talking about the results, I do want to jump to the later part of the slides. So remember, this part starts to show that, okay, we shouldn't be working with the average learning like response time. We should really looking at individuals. So that's when, well, hierarchical model is even more needed. And so just refresh your memory here really quick. This is like the, I think one, like the, how can I put it, right? About the details, but one is the learning, like the blue one on the top, the blue greenish. That's the learning. No, sorry. That's the word. That's for the word N, which is the start of the, like the first element of the triple. Okay, and then because W we know is NIW. That's always appearing that way. So for some people, which they're going to be clustered as learners, you're just going to have a shorter response time for that, and then that's being trying to be captured by this model in red. And as you can see, it has the similar beginnings like feature, but then all of a sudden you have this onset, learning onset, which is trying to be captured by omega. And then that's something like one extra element that you multiply to the power function. You can think of the power function of power function together, and then that's just gonna get it like dropping even faster. So they came up with this model, and then of course you get a few more parameters that you want to estimate, and then they're going to start to share those parameters in the model again. Okay? So this, I think, is the outcome. So for, I remember last time we were saying that the top panel, the top panel are the ones that are not being classified as learners. So they're learning, I mean, if you think about the response time, like doesn't really change much. Whereas the middle one is sort of having 50% of being classified as learners. So you start to see some change, okay? Whereas the last panel, the bottom three, are subjects, I mean, certain subjects are having like being a learner probability as 1, and you can see how the data looks so different, I mean, how the behavior of those stars are. Okay? So then they talked about, so this is something we mentioned earlier at the beginning of this unit, but didn't get into it too much. So this is the cases or plots or summaries, new summaries, which I don't think we've done much yet, of looking at the posterior estimation. Okay, so these are like showing you the beta, which is the amount of learning, and gamma, I think they define as to be the speed of learning, and omega is the onset of learning. So all of this are in that power function, and then that's, I think, the meaning in the learning theory, how they're defining it in terms of the model. So then you can see the breakdown. They're color-coded by the different conditions, the known words, the novel words, and scrambled words. Now remember in the video, Josh was talking about that for beta and gamma, you don't really see much a difference in some sense across the different conditions or contexts. However, if you look at the onset of learning, then you see, I would say overall, like there are more variability in the first place when you're thinking about the red ones, which is for the known word. And by the way, I should also mention, he talked about that in his video, which might be new to you. I think it's like say, looking at this. So I think that's they're returning a 95% credible interval for each of the point estimate for the parameter. And then the dot in the middle, I think, it's the mean. Okay, so this is another way to represent, like you can look at the variability, not only the point estimate, which are the dots, but also the uncertainty estimate on the same plot. Okay, and then of course the wider those straight line are, the higher the variability. And then you can start to see that the onset for those ones is very, very much concentrated. Okay?
meaning that very few variability in terms of that parameter. And I think that's true for all of the words. I mean, for the onset of learning case, whereas you can see a lot of overlapping in those other cases. So those, again, I think in the context will have to be very important to interpret. Again, I don't really understand too much of the learning theory that they're talking about, so I couldn't have too much more, I guess, insight about this. But just looking at the way that they summarize and then how they behave differently, I think it's interesting and important for us to keep in mind that all of the parameters that you set up in your model, they're meaningful. And then later when you're trying to summarize their posterior, it's not that just run the model and then it's done. It's more about, okay, I've run this model. What does this model tell me about what I can learn from this data for, in this case, the learning theory that they're trying to make inference about. Okay. And one last thing, which is also very nice, I think in computer science, they do a lot of this kind of plotting, which is cool. So this, if you remember that I mentioned it as a question, and now I still don't know the answer is, I think for the second part of the model that they are fitting a learner status, I would say, or like a probability of being a learner for each person, I think, subject in the data. So, and then in the end, they are actually able to, I think for each condition, they're able to summarize, my understanding is summarizing, of the probability of being classified as a learner for a different condition. Okay. So let's just focus on the left for a minute. So it's for the known words, the novel words, and then the scrambled. And you can see that they're plotting the they plot the histogram, which is the probability. So it's going to be between 0 and 1. And they're plotting also something they call 95% HDI. So that's a term that we never talked about before, but it's actually pretty intuitive. So let me just show you really quickly what it is. So when we summarize, remember when we are making parameter draws, posterior draws, let's say mu in our model, like mu in the normal model, okay, whatever that is. And then you have posterior draws of them from Gibbs or even just from Monte Carlo, depends on what kind of models you're doing. So typically what we're saying, we have like a large number of draws and then we plot them and then you can get, say, like a middle 95% credible interval. What you do is you use the quantile function, right? You have a lot of draws and then you get the middle, right? So, so that's usually what we call credible interval. And you notice that I always try to emphasize that it's the middle 95 credible interval, because when we're returning it, we use what? We use quantile function. Say whatever, like the mu samples. And then you write what? 0.025, right? And then 0.975 to return the middle 95. Okay? Yeah. So that's getting the middle ones. And another way, sometimes more popular, I would say, to summarize the posterior is not looking at like percentile-wise, but thinking about what is most likely. So for example, if you have a density, like if you try to like plot the mu's in the histogram and then put a density on top of it, let's say the shape is like this. Let's just say, I don't know exactly how it will look like, just say it looks like this. So if you try to, I mean, in this case, if you try to like cut and getting the middle 95, well, probably like no big difference if you do this or do HDI. I will talk about what HDI is in a minute. So HDI stands for highest density interval. So the way that they come up with this, they're like available function to do it. The point is, well, I know this is, say, like the density of my posterior draws or like, yeah, the samples, and I only want the highest 95%. Okay, it's not that I care about the middle. I know the middle like tells me about something, middle. And but I want to get the highest, probably like the range of the highest, like the highest 95% range of my posterior. So the way to get it is you have a vertical line on top, and you keep dropping it, because the density tells us what the density, like the higher, like say the taller the density, like say this point is having a higher density than that point, right? A and B, let me just say A is having a higher density than B. So the way that you get this HDI is you have this curve horizontal, and they just keep dropping it, and you stop when you get exactly, so bad drawing, sorry, but you stop when you get exactly 95 above. Okay, so that gives you the highest density interval in contrast to the credible interval that we do. And sometimes people like to report that more than the credible interval, because they want to give you or get a sense of the range of, say, the parameter draws, the parameter values that has the highest posterior density. So that's what they use. I think HDI. I think it stands for that. I know the meaning, but I'm not sure. I think HDI stands for highest density interval. Yeah. All right. So that's what they're returning. Now let's go back here. That's what they're returning those. Okay. But again, it's a credible interval in some sense. All right. So so now let's focus on the left. What does this tell us? The three plots. Known words, the novel words, and then the scrambled words. This is looking at the probability of classifying someone as a learner in that condition. I mean, for the different conditions. What do you think that tells us? And if you get some idea, also come back here. That's the omega in the model. They call it as the onset of learning. I think just means like the starting point of the learning itself. And you can see that for different conditions, they behave so differently. And it's very important. I think it's very smart and neat that they are doing the plotting like one by one and put it together. And the x-axis, I mean, it's the same range. So it's much easier for you to visualize the differences in those parameter estimates. Okay, so I will pause here for a few minutes. You can talk to your neighbors about this, and then we're going to do the lab. Yeah, also really quick, not only just thinking about like their locations, but also their spread, because that tells us something else as well, okay, when you're looking at those plots. Yeah. Any comment?
Yeah.
Like either the learner probability or the onset, whichever is fine. If you want to make a comment about different conditions, and then, well, does it make sense to you that like the locations of like say the learner probability are very different, and whether it makes sense to you that the locations are different and the spread slightly different as well, whereas on the onset I think not only the locations but the spread are pretty different across the different conditions as well. Any ideas, or like surprising or not so much? Yeah, Kenneth?
One surprising thing that we noticed is that the onset of learning for the numbers is such a small interval.
For the known words?
Yeah.
Mm-hmm, mm-hmm.
And I guess I was wondering why, like maybe from a cognitive science side, why it's so narrow. Like, what is it that between the 16 and the 19 time?
Right. So what does it mean that it's so narrow? Just in the context, what does it mean? Yeah, I'm asking.
That I guess 95% of the people taking the test begin to learn at that interval.
Mm-hmm.
Or like that's when the curve starts to decrease.
Right. Whereas I guess for the scrambled, it's later, obviously. It's around 40, but it's also wider, right? Yeah. Well, anyway.
Is that also like people picked it up generally around the same time points? Like it didn't take some people longer?
Right. let's see. So, right, because that omega is trying to capture the learning time. I mean, the time that you start to learn, the onset. So, if it's shorter interval comparing to the other ones, you're just saying that, well, for that condition, most people like pick up around the same time. I sort of agree. Yeah.
Isn't it also like the spread for like the known words is smaller because more people were learners in the known words category?
Good question. I never know the sample size. Do we ever know the sample size? I don't know.
Well, I'm
Or,
just saying
like,
like the
what can you-
probability that they are a learner is higher in the
Mhm.
known words category.
Oh, you mean
And don't you have to be a
for this-
learner to be, you know, have an onset of learning for the second half?
I see what you mean. What do you guys think? I don't understand the model well enough to say that, but so Dahlia's point is you have to be a learner, otherwise you don't even have the onset. I think if I have to guess, I think that's true. I just don't know well enough to make the comments, but that's good. So you're saying that then that might make it less variable because there are more
people will be learners just based on the probability.
Mm-hmm. Oh, I see what you mean. So suppose if they're a fixed number, the same number of okay, now I get it. Okay, yeah. So if it's the same number of people in each of the condition, and then if we look at the left-hand side, we can see that well, there will be more people classified as learners in the known word condition, just based on the probability, right? If you have 100 in each case, in each condition, then for the known words you have about 70% of them, roughly, like the mean, the mode there. And then for the novel words, it's only 30%, and then for the scrambled words, it's even less than 20%, right? So it's, let's say 70, 30, and 20 people in each group. And then, because you slightly have a larger, yeah, I wonder if the sample size will matter in that case. But I see your point now, because there are more people classified as learners in the known words condition, so then the spread of that onset of learning might be smaller than the other ones. Good point. Yeah. Yeah. Interesting. I never thought it that way. Mm-hmm.
When you see a spike at 0.
Hmm?
I'm just thinking, when you see a spike at 0, a lot of people aren't classified as learners in the major conditions.
I'm saying that they wouldn't be included.
In the onset?
Yes, because an onset of 0 would mean that they learned at time 0. I think, anyway. That's my understanding.
Mm-hmm. Good point. So let's go back. So keep this in mind. And if we go back to the model that they presented, which is this one, right? So if omega is 0, oh, I couldn't tell. Can we tell anything about if omega is 0 in this case? Still hard to say. So multiplying. Let's see. Yeah, I don't know. Well, like, what does it mean to have omega in this case? But I do remember if the beta learn is 0, then the person is not a learner. Right? Because then that whole multiplied term, the second line in red on the right-hand side, becomes 1. So it becomes the original, the same model as before. But, well, yeah, I don't know. The omega, what does it mean in the model? But good observation. Anything else about this? Okay, all right. If not, okay. We're gonna stop this here, and then not so much time left, but we can work on the